Good morning. Let's start our review this morning. And I'm going to just first talk a little bit about the power transmission project. And then we're going to spend some time discussing the exam solutions for the midterm, because it's very important that we learn from the exam. Lessons learned are very important, and they will guide us as we move on to the final. So let's first look at the power transmission project. As I mentioned, there's going to be a requirement that we would have only one report at the end of the term, at the end of this quarter. And the report is outlined here. You have a guide as a manual that was prepared by Andrew Sheng, the TA. And it goes through three different areas. And I think we are at the point where we can start actually working. The same teams can work on the same project together to make up the final report. So there's not going to be a progress report here, because it's, as I mentioned, it's like a very long homework assignment. So the project is three distinct areas. The first one is to determine the gears, the sizes, the materials, the number of teeth, and the arrangements to fulfill a 90-degree power transmission. And that comes from the horsepower that is to be transmitted, and the RPM reduction ratio, as we discussed before. And so this is the first step, and I think most of us can do this step right now. Then the second step is to analyze the survivability of the gears. And that can wait a little bit as we fill in more equations required for the gear lifetime. So the survival of the gears, whether they're going to take all of these loads, even after we have chosen the number of teeth and the sizes, will depend on the power that is transmitted, and that translates to torques on the gears, and that translates to forces on the teeth. And the forces lead to two things. One is wear, and there are some formulas for wear that we will refer to. And the other one is for fatigue, and that is from bending, because we would have like a bending force on the gear teeth. So I think that part, it can wait a little bit until we fill in some more of the course information. So that's the gears. It's the section of the gears. The next section is on the shafts. And the shafts, we have several shafts to make that transmission. And each one, we would need to select the size. And the size would be stepped, because we have to attach the gears. And the stepping is to locate the gears precisely. We have to have a shoulder, so we have from small to large size. And then we would have also to have grooves to attach retaining rings or set screws or other features that will ensure that the gears can be assembled and disassembled easily. So the shaft design is at hand right now, because we know how to go from power to torque to forces, and how to find reactions, and how to make the shear force diagrams, how to make the bending moment diagrams, and that will go for the three shafts that we would have to design or more. And once, so this is a statics problem, so a long statics problem. And then we would have to do the deflection. So we have done the calculations for the moments. Then we would have to do the deflections. And the deflections, we would like to use a MATLAB code that I posted online. And the reason is that the analytical formulas that we developed are for uniform dimensions of the shaft. So the shaft dimensions do not change as a function of location. But if the shaft is stepped various sizes, then it would be much easier to use kind of a numerical method. And I have the numerical method, so it would be very good practice for you to review what this numerical method entails. Is based on the material that we've covered in class, and I have a video on it. But the program, that's MATLAB program, you can download it and actually put in your information and run it. Then it will give you the deflections all along the shaft, and then you can decide whether these deflections are consistent with the ASME criteria for maximum deflections. And also we have to determine the twist angle from the torques, and find out if the angle of twist is also consistent with the design requirements. So that part of the shaft analysis we can do right away. Then the last part of the shaft analysis is to determine the lifetime of the shaft due to fatigue or static. So first we would do static loading, and right now we are finishing a chapter on static lifetime assessment based on either ductile or brittle failure theories. So we could use one of these theories, maybe distortion energy criteria, or we could use maximum shear, for example, and then determine the factor of safety against static loading. In the next week or so, we would have enough information on fatigue to complete that part of the project and determine the fatigue lifetime based on the SN diagram and the strength versus number of cycles to failure criteria. So that will complete the shaft analysis. So as I said, gears, shafts, and then the last part is the attachments. And these are the bearings, the keys, the retaining rings, and those are, we have the formulas in the book, and we would want to make sure that the stress concentration factors introduced by the retaining rings or the set screws or by the keys do not actually lead to extra stresses that can lead to failure, even though we have assured that fatigue lifetime is, say, infinite lifetime. According to our analysis, it could turn out to be not the case if these locations bring in very high stress concentrations. So again, you have these three elements, and then at the end, we would assemble all of that and maybe make a CAD drawing. And 3D would be preferred if you have experience with SolidWorks or others. Then you can put it together with the exact dimensions. So you have everything here. The only thing remaining in this manual that I didn't see Andrew prepare is the fatigue lifetime, and that we can follow the chapter 18. So if you go through this one by one, you are ready now to kind of take some elements. I think I asked him to put in some snippets of MATLAB script, so it guides us, but you're free to write your own script because all of the equations are there. It's just basically we're writing it in MATLAB to make it easier for us to do the calculations. But he made it very organized. What is the input? What's the output? And the reason for that is that by mimicking something that is made, program, then we become better programmers and we can do the job much more efficiently. So you have all of this here. I'd like you to go through it. And then what we wanted to do is follow Chapter 18. And Chapter 18 is the one that goes through the calculations, so you can have a feel of the calculations by hand. You would see which equations we have covered, which equations we still need to kind of review, or we have to kind of look up on our own. So the Chapter 18 is right there. It's an example. The way I look at it is a very long, very long homework assignment, because it goes through everything in the course, and it goes through the calculations for the reduction ratio and how you split it into stages, and then how you guarantee the minimum number of teeth in one of the gears, and that sets the motion to calculations for all of the torques and the speeds, intermediate speeds, and selection for the number of teeth. And then once that is done, we have some specific constraint on the size, and that can set the pitch of the gears. And the pitch of the gears, of course, can tell us the size, which will determine the strength of the gear. If it is maybe not too strong, not too beefy, the gear itself may not take the forces. So that we have to also consider what they call the face width, because the gear has a pitch which determines the height, but also you can have it go deeper or shallower. So you can have a skinny gear or a very beefy gear, and that all depends on how you want to take the forces and the torques on the system. So I would ask you to go through that part, like up to here. This is case study part 3, gear specifications. And then you can, the things that the wear calculations and the bending calculations for the gears, we can wait a little bit to do that in a few weeks. But we can go on to do the shaft layout. And the shaft layout, we have one part of it is to kind of make a sketch like that, but in your case will be different, and then translate the sketch to some dimensions, and you go at it with the shear force diagram, bending moment diagrams, and you add stress concentration factors, and then you start calculating diameters in a similar way to what we've done so far. And you will see that even in the midterm, we're going to refer to that a little bit. So that would be connecting to what we've done in the midterm. So this is as far as we want to review for this speed reduction project, or the gearbox project. And what I wanted to do now is review step by step the different problems that we had in the midterm, and it would be good if we can have a discussion and questions to learn from the little tricks that can make it easier for us on the final. So that's what we need to do. It's just kind of little tricks that can make it more efficient, more direct, and less time consuming. So the first question that we wanted to have a shaft, but the shaft has to transmit 150 horsepower at 4,000 RPM. So it's a kind of an elementary part of shaft design, as you will do much more extensively in your second project. So this is 150 horsepower. We're given two numbers, horsepower and the RPM. From that, we should be able to determine the torque for sure. and the torque means some force, right? So you have something on the shaft, and usually the topic for design of the shaft is the selection of the diameter of the shaft, as you will see in this extensive design project. Now, the additional little twist in there, if it were just straightforward calculation that we have the torque and we can calculate the diameter of the shaft and the torque given a maximum allowable shear stress. So the calculation would have proceeded like this. We would have the second moment of area. We have the polar moment of area, which is half. Everybody knows that. We can get the torque from the horsepower. We have the formula to do that. Here it is a little bit more detailed, going horsepower to divided. This is the SI version, which is without any units, and these are the units of the conversion. You convert horsepower to RPM on RPM. Then you have to go how you convert 1 horsepower to foot-pound per second, and then revolution to 2 pi radian and seconds to minute. So you could do that, or you just use the formula that we have. Some of you opted to choose to use SI units, but that led to some errors, numerical errors. But if you use the formula for horsepower to RPM directly to torque in foot-pound, then most of you got that answer, 2363. So that's fine. So we have some number here. And then if we are designing the shaft to resist torsion alone, then there'll be no problem because we have the maximum shear is 40 KSI, and we just calculate the actual shear in the shaft, which is TR over J, and then make sure that the actual shear is not bigger than the max allowable, or we can just equate them, assuming that we have a factor of safety of 1. And so many of you, I think the majority did that. The problem with this is that we do not consider additional aspects that can lead to overstress. And that aspect is that when we attach gears, as you'll see in the project, the gears produce forces either down or up on the shaft or transverse where they are attached. And the forces produce a moment. So the moment that we have here is 336 foot-pound. So when we have a moment, the moment produces a tensile force on the bottom and compressive on the top, a maximum at the top or bottom fibers. And then we just kind of try to see, if there is something that this can lead to failure. So that gets us to the idea of failure theories. And the idea of failure theories is that we're not considering the shear stress. We would like to know what is the maximum shear stress. And the maximum shear stress, as we know from Mohr circle, is not the actual shear. We have to kind of rotate the angle until we find a situation that we have pure shear, or pure shear and some tension compression, which is the radius of the Mohr circle. And that's the radius of the Mohr circle is the maximum shear. So the failure criterion is based on the maximum shear. So if we look at here, the allowable stress is 40 KSI. That allowable stress is for the maximum shear. And therefore, we must calculate whatever normal stresses there is. Here we have bending. Obviously, if we have another axial force, we could have made another axial force, tension, compression. Then we have to add that to the picture. And then we use the Mohr circle analysis. And in this case, we got trained so much that the Mohr circle, if we want to find the radius, is the square root of sigma x minus sigma y over 2 squared plus the tau squared. So here we don't have a sigma y, so it'll be sigma x over 2 squared, which is the one from bending, and then this is the actual coming from the torsion. So if we don't know the diameter, we can leave everything in terms of the radius and then solve for the radius and hence the diameter. So the answer here came to be 0.84 inch because we had to resist the bending. For those of us who did only torsion, the answer was 0.6. So you can see from 0.6 to 0.8, you need to add a little bit, you make a shaft a little bit beefier so that you can actually resist both torsion and bending. Please stop me if you have any questions as we move on. So, and that brings me to the last part. So there's the last part of the question was finding the principal stresses. And the principal stresses is another way to look at failure. So when you see the term principal stresses, triggers in our mind that we have a triaxial stress state generally, and we want to just pick either the maximum shear, which is what we did before, or the principal stresses. The reason is always that failure is based on maximum shear or on the principal stresses. So here we have the two principal stresses, we can find them, and these can be used if the shaft is made of a brittle material, like maybe cast iron, then the failure would be based on the principal stresses. But we didn't ask that. Finally, the angle of twist. This is TL over GJ. This is, I think, all of us, or most of us did it right. And that determines, if you see the angle of twist, if you have a shaft and you twist it, as you make it longer and longer and longer, then you can twist it more. That's the idea. So the idea here is L here is a controlling factor. So in ASME standards, we can't just have a shaft that twists too much, right? So there's a limit, very, very small limit actually. I put this as 0.2 degrees, but actually it could be down to 0.02 or 0.002 degrees if you want to have a stiff shaft in a very precise machine. So that number controls the length of the shaft. Here, the length of the shaft came to be kind of ridiculously small, 0.84 inches, and the reason is the angle of twist is too sloppy. 0.2 degrees is too much to allow for. Okay. The next question was more qualitative, and one part was from chapter 1, and I'd like to discuss that. So the idea for qualitative questions is that there's some information in the book that are of nature of background information or useful information for material selection or for material properties or for shaft characteristics or configurations. These are things that don't have mathematics, right? So we need to kind of be able to read them and absorb them and still be useful for us as engineers. So we asked one question on the families and classes within families. So a family is like a metal or a ceramic or a hybrid. These are the families that we have 7 family glasses. We have 7 families and families. And then within each family, we have classes. So we say metal, we have iron alloys, or going from steels, cast iron, all of this. Nickel-based alloys, we have copper-based alloys, we have aluminum-based. So these are all kind of classes within the family. So this is very qualitative, and a lot of us got that right. Then the next one is what is cold work? And when we ask the question about a definition, it would be useful to have a diagram. Like you can say what is cold work, or you can write an equation for it, but it's always useful to have a diagram to illustrate it. So in this case here, we have the equation is the reduction area divided by the original area, and then we can define loading and unloading, and then reloading. When you reload it, then you make it stronger, and then you can talk about this increased strength as a result of the cold work. Then the next one is a pin that is to be inserted in a clevis, and we have a snap ring to go on the pin. So if you look at the pin here, it has a size that is unknown, and the allowance also the precision is to be also established, right? So the tolerance. So here we have the clevis. It has an average size and a tolerance. The snap ring has an average size and a tolerance. So these come from the manufacturing step, that the clevis and the snap ring, you produce it in thousands and millions, and then you have statistical analysis. Somebody comes and does the measurements and then give you like a Gaussian distribution, and that is the standard deviation that defined, right? So now you want to order a pin, right? So you want to order a pin from another manufacturer. So the pin the manufacturer is going to have to certify that has an average value and a standard deviation. So how do you do that? Well, the average value, the A, has to be the average, the sum of the average value of the clevis and the average value of the snap ring and the average value of the gap. So we need to have a gap. And the gap is, by design, is required to have dimensions no less than 5 mils and no more than 60 mils. That's by design because of precision. So the gap is already kind of specified. So what is unknown here is the averages and the tolerance in the pin. And therefore, what we have to do is that the average in the pin is obviously the 1.5 plus the average in the gap, which is medium between 5 mils and 60 mils. You just take the median between these two numbers, and also the average in the snap ring. So there's no problem. To get the tolerance here, we now have to realize that the tolerance in the gap is the result of tolerances in the snap ring and the clevis and the pin. And therefore, and the tolerances, when we do statistics, we add the tolerances because we add the standard deviations. So the analysis is that the average, so we get the mean value of the gap size to be 32.5 mils, and the tolerance is the difference between the maximum and the average value. We get 27.5 mils, and then the clevis, the nominal value of the clevis is the sum, of course, of these three numbers. And then what we do is that the gap now is, although the gap is the difference between A and all of the other two, but the tolerance is going to be the sum of all of the tolerances because it is controlled by statistics of independent random variables. And the independent random variables are for the pin and for the clevis and for the snap ring. And this way we can determine the tolerance in the pin. Okay, next problem that we have is a Castagliano deflection problem. This is also typical in the course. We learned Castagliano, and the reason we did learn it is that a lot of times we just don't want to have the headache of starting from the shear force diagram, bending moment diagram, integrate another time and find a deflection everywhere and all of that. So Castigliano, the idea behind it is that it's a quick way to find deflection where you really think you need it. So in this case, you don't waste time to do all of the statics and integrations. The drawback of Castigliano, if there's one, is that we have to be careful in what constitutes the elastic energy stored in the structure. And once we find that out, then we have to take a derivative of the elastic energy with respect to the force under which we need the deflection. So conceptually, it sounds simple, right? But the implementation is a little bit needs more practice. So it's just basically, it needs a few problem solving. So we would know how to do it quick. In this example, we have a force here that, excuse me. So we have a force that is acting on a shaft and making a deflection. And the deflection is due to the bending of this little shaft. So we know that the bending is going to be the major part where the energy is going to be stored. But if we think a little bit carefully, as this shaft deflects, then the torque tube that is connected, which is stepped, will also have to twist. And then when the tube twists, it has two sections, AC and CD. Each section will have to do some work, and when it does work, it means it's going to store elastic energy. So it's going to be elastic energy stored here, elastic energy stored here, and elastic energy stored in bending. So I thought about this way. Then I'm going to start also thinking a little bit carefully to predict that the energy stored in bending is going to be the highest, because this is where most of the bending is going to cause deflection. And then we have a thin part of the shaft that is going to twist a lot because it's small, and therefore it will store more energy. And then we have a thick part of the shaft, so it's not going to twist a lot, and therefore it's going to store less. So I predict that the energy stored in this CO is going to be small, and the energy stored in AC is going to be kind of medium, and the energy stored in AB in bending is going to be large. And then I have to add the contributions of these three and take the derivative. So before I even do the problem, if it happened to be that AC and CO are rigid, completely rigid, they don't really move at all, then the energy is going to be stored in bending, and we have a force on a cantilever. And we know from our experience that if you have a force on a cantilever, then the deflection is FL cubed over 3EI. That's kind of a formula that we used over and over again. If you just have a cantilever, a force, that's a formula that you should remember. So it should come out something along these lines. So all of this just in preparation. So I have to do the second moment of area because I need it for bending, the polar moments of areas for the two sections that will twist. And then in the integrations, formulas we have to prepare two things, the moment or the torque, and the derivative of the moment or the torque with respect to the force. So when I do that, I have to be careful where I put the coordinate system. For example, if I put the coordinate system at A, then the force here, I have to consider one generic point moving along here, so X is here. Then the moment is going to be a function of 0.2 minus x. So the moment would be f times 0.2 minus x. And then we take the derivative, would be 0.2 minus x, and then it's going to just take a lot more calculations. So another way is to put the coordinate system under f. So if I put it under f and I go the other way around, so the moment will be just f times x. And that's what we have here. So it'll be easier, f times x. And then I take the derivative, it gives me x. So inside we get x squared. And then when we integrate x squared, we get x cubed over 3. So the 3 pops down here, and you get FL cubed over 3EI, which is kind of the standard formula that we know. But here you see how it is derived very easily from the Castagliano idea. Now the torques are different because the torque is the force times LAB and F times L. So this is LAB is fixed. So the torque along the tubes here is constant. So great, you know, if the torque is also a function of x, then we have to do some integration with respect to x. But luckily, the torque is the same everywhere, and therefore the integrations will be rather quick and easy. So we have F times LAB. When we take the derivative with respect to F, we get L, and therefore the integration will be just integration over the length of the tube, and you get this generic formula, and then you substitute everything in terms of F for the 2 sections. And then when you calculate the displacement, it is the sum of the 3 displacements that we mentioned. So now, as we try to use common sense, we see the tube that is twisting, 9.6 times 10 minus 6 F. The smaller size tube for under twist is 48 times 10 minus 6. So as we expected, it's a lot. And then the bending is 1.92 times 10 minus 4, which is maybe an order of magnitude larger than any of these 2 contributions. So we get the result very close to what we would get from bending. So 2.5, and the bending alone is 1.92. So the torsion part added like another 0.5 times 10 minus 4. So it's like, 25% more deflection due to the energy in the torsion. Okay. And then the spring rate is F over delta. And then when you do that calculation, what I notice is that many of us does not pay attention to the units. So we have to pay attention to the units. If we do things in meter and Newton and, get away from pounds and stuff like that. So here everything is, millimeter. So we have to convert it to meters. Then the result will be in Newton per meter. And here the result will be, the rate is kilonewton per meter. Now problem 4 is a problem that is representative of some kind of a distribution of loading on a beam of somewhat general cross-section. And the designer is asked to determine the factor of safety against failure, which means that it's gonna go through steps. Step 1 is figuring out shear forces, because part of the failure is going to be maximum shear, and the maximum shear is not the transverse shear. It is a combination of the transverse shear and the normal stress resulting from bending, right? Like we did in the shaft. So we have to get the shear distribution and find out where is the maximum shear. Then next, we want to find the bending moment distribution and find out where is the maximum bending moment. And then we have to investigate at the maximum bending moment, what is the normal stress and what is the corresponding maximum shear. And then at the maximum transverse shear location, what is the shear stress from that transverse shear, and what is the maximum shear stress if we add the bending contribution. So this is kind of the idea of the problem. So I think majority did correctly the distribution. So 3,000 here will be shear down, and then it be reacted by the sum of the 3,000 and the 600 times 30. So very simple to have reaction 1,300, and therefore the shear force diagram looks like this. Will be 3,000 down, and then boom, 1,300 up, and then as you add now the little forces coming down, 600 pound-foot per inch. That's like a slope. So that slope 600 will bring down that number to 0 at some point here, and negative at the end of the beam. So all of us, I would say, did that. So now, before we proceed, you can write now you can write an equation like that, and this equation is a reflection of the diagram that you make, right? So if we run the equation will have to be Heaviside unit step function at x equals 10, and so it's going up, and then you have to because we have a step up, and then we have to also have a linear function, which is this one, with a slope of 600, so 600 times x, but the x is shifted to to 10, so it's x minus 10 times Heaviside at x minus 10. So the Heaviside meaning the what we learned in singularity functions, and it's like power of 1, and then we can integrate it and proceed, to get the distribution. So this is one way. Another way is just kind of to be a little bit clever about it and figure out, I'm just not really looking for distributions. I'm looking for where things can go wrong. So things can go wrong would be at x equals 10. This is the largest transverse shear force, so it's going to lead to high shear stress. So and that is known already because we know the shear force here. And then I'm looking for the maximum moment. The maximum moment, as we will see, the moment is the integration of the shear force distribution. So if you integrate the shear force distribution as linear, then the linear integration of linear is parabolic. So you have a parabola. Integration of constant, you have a straight line. So you would imagine that you have a straight line, negative, and then you have a parabola coming out, and the parabola has a maximum. And the maximum parabola is when the slope is 0, because the shear force has a 0 value here. So the 0 value would correspond to the maximum. And I think several of you have realized that, and that led to great simplification. So instead of doing the integrations, then you just find the value of the moment at that point. By whatever means, you just kind of take the moments and find at that point to get that number here. So this is the maximum moment that you have. So we got that number here, and then we got that number here. And these are the two numbers that actually count to find the required shear stresses and maximum shears. So that number here is obtained from a straight line. So instead of even working on this equation, I can just make a straight line here and find the solution from the slope at that point, and this is what we did here. So this is the slope, the distance divided by slope plus the shift. You get the point of the maximum, and then you find the bending moment maximum. And then the next part of the problem, I would have to agree this is a longer problem, but it's kind of balanced the rest of the exam. So we have to find the geometric properties, finding the average, the centroidal position in the beam, finding the total moment of area, of second moment of area, by finding the moment of area of the thin section, moment of area of the flange and the web, and adding them together and using the parallel axis theorem to do the transfer of the moments, second moments. So I would urge those of you who are a little bit rusty on that to be able to do this calculation quickly, but most of us did. And then once I know the location of the common centroid, it's minus 1.75. So there's a kind of asymmetry. The top part of the beam has a compressive stress 5,000, and the bottom part has a tensile stress. The bottom. Sorry, the 1.75 is closer to the bottom. So if you look at it, the centroid is going to be right here. So if you calculate the stress in the bottom, it's going to be small. At the top is going to be high. And these are the two numbers that we have here. So this is the number that we have here, compressive stress. And then we look at the critical locations. And the critical locations are either going to be at this point or going to be at this point, at x equals 10 or x equals 26.7. So we investigate that x equals 26.7, and our investigation is based on the maximum shear. So maximum shear, we have things are varying on the cross section. So right in the center of the beam or the centroid, there's no bending stress, but the shear stress is the largest, right? However, the value of the shear force at that location is 0, so it doesn't matter. So everything is just based on tensile or compressive stress. However, I'm looking for maximum shear. Maximum shear in this case is the radius of the Mohr circle, which is half of the value of the principal stress, which is now the compressive 9541. Now I shift to x equals 10, and there I have to check two locations. One is location at the flange web intersection, and the other one is at the centroid. So I do the VQ over IB, and I compare the maximum at these locations. And when I do that, I have to combine the bending moment effect in a Mohr circle type calculation to determine the largest shear, and gives us the factor of safety. So if I analyze this problem, I would say it is, again, requires understanding of the meaning of maximum shear versus transverse shear, understanding how to do things quickly to locate where things can go wrong without doing, integrations and things like that. So it takes a little bit of cleverness in doing that, and also dexterity with the properties of cross sections, like this kind of calculation. If you do it quick, then you have more time to resolve the problem. So I think from a design standpoint, it's more of a calculational problem. Of course, probably all of us know how to do it kind of conceptually, but part of the training is to do it efficiently, accurately, and with the least amount of effort. Then the last problem was a bonus problem, and it's kind of a cleverness problem, right? It's of this variety. So the problem is that we have two shafts that are pulled, and the tip at C is pulled by 5, like a concentrated force of 5 kilopounds, and at B is 3 kilopounds. So we have 5 pulling on C and 5 pulling on at B, exactly at B, and then there's a gap. So if the pull is so large, then it's going to bounce against the gap, and then there's going to be a reaction from the wall that would modify these forces. So if I think about it, I have to think like, if I'm an element inside here, so if I'm an element at the shaft BC, I'm going to see a force before it hits the wall. I'm going to see a force to the right of 5. Then the element has to be balanced, which means that the force to the left is going to be also 5, which means that from B to C, the force that I'll see if I insert my hand inside for some reason, the force on my hand is going to be 5 kip. Then if I move now a little bit slightly left to B, I would see that there's a pull of 5 and then an additional pull of 3. And therefore, the element within AB is going to see a force of 8. So if I have a force distribution, it's going to be 5 here, and then a step, and then 8 here. I would say 50% of those attempted, they did not see that the force in AB it would be 8. They left it as 3. But as you can see from equilibrium standpoint, this wall here has to react by 8 because you have 5 here and 3 here, then you have to react by 8, which means that it has to be 5 and stepping to 8, right? So if you know the forces, then all of us know the formula, F L over AE, and you do this for here, and for here you add them up, and you see how far they extend. So you need the elastic modulus, basically, which is, we have some, you can assume a steel, and then you can calculate the displacement, and you figure out that it's greater than 5 mils. So it means that these two are going to go against the wall. Now, the second part of the problem is the wall is going to push back, and when it pushes back, it will modify the forces here, and also it's going to produce stresses. So there'll be a stress here and a stress here, and we want to find the stresses in there. So in this case, the 5 is going to have a reaction against it. So the force in BC will be 5 minus that reaction. And the force in AB will be 8 minus this reaction. And then you resolve the problem to determine the reaction. Now that you know the total displacement is exactly 5 mils. So that's the first part, is 8 and 5. You get 26 mil. This is greater. So now the second part is subtract the reaction. And then we find the force. It turns out to be 5.06 kip. And then once we determine, then we can calculate the stresses in the two sections. One would be compression, one would be tension, right? So that's kind of an interesting problem. And if I were to think about any variation myself, I would say, what if we have this system at, let's say, temperature T1, and then I heated it up to temperature T2. Same thing. So you can calculate the expansion in the tube, and if the walls are rigid, you can also set up the forces from the wall, and then you have the constraint would be the size of the gap is given, and therefore you can calculate thermal stresses in that case. So you can see variations on this. There could be thermal stresses, it could be additional forces on it, but it is kind of, one has to think about the ideas of equilibrium in every section in there. So I think this is what I have here, and I'd like to see if there are any questions as we progress through the course or any other issues. I did grade all of the homework assignments, and not the homework assignments, rather the midterm exam, and just to see how we did on the midterm. Several have gotten almost 100%. Some didn't do as well. And the grades that we have, we had an average on the midterm of almost 75%, 74.3, which is quite good, given that the midterm is a part of the grade, and then this course has more components on the design projects, so we have push a little bit harder on the design to kind of get a good grade on the final. And I also graded the progress report, and the progress report is out of 15 points from the project total. So because we have the final for the connecting rod is 55 points, and then we have the second project on the gearbox, which is 30 points. So out of the 15, the average has been 13.36, which is also quite good. There are several who did extremely well, going all the way to finite element and doing more work on the optimization, material selection. Was clear that they looked at the literature carefully, and they did put enough effort. Some didn't have enough time to do the finite elements, so I hope that we can push a little bit more to finalize that project. Okay, so this is where we are, and I hope everybody's doing well, and see if you guys have any questions. Okay, so if there are no questions, I think this will.
I have a question.
Okay, go ahead.
Did you say the final was going to be cumulative?
Yeah, the final is going to be cumulative on the course, but with more emphasis on the material after the midterm. So as we move on, there's going to be more emphasis on static failure theories, fatigue, and then shaft design and the gears. And very little is going to be before the midterm. And the final is going to be open book, so you'll have the formulas and the charts available from the book.
All right, thank you.
You're welcome. Okay, so everybody have a good weekend, and we'll see you next week.